All right, normally when we would connect the thermocouple up to a transmitter, you guys, these transmitters look just like the ones we did for RTDs. They're the hockey puck looking devices. You would have an input side, the sensor side, and this is polarity sensitive. There is a positive lead and a negative lead on the thermocouple itself. And it's going to be indicated by a symbol like this, a little wiring diagram on the transmitter itself like that. Then the outside leads, the output leads, are the same that we had before. It's going to be something like that. And we have a zero adjustment and a span adjustment. We have to because we calibrate these things for a set amount of temperature difference between your lower range value and your upper range value. And you remember that the zero was for your lower range value and your span was for your upper range value. And these are found on the little data sticker that's on the transmitter itself. And if we had a real thermocouple, we would just simply connect the wires from that thermocouple together on the transmitter itself. We would connect it like that. Then on the output side, it's still a current loop. It is still your power supply, your current meter to measure what the current is going through there on your output side, because it still has to be 4 to 20 milliamps. This is still set on milliamps. We still follow the same rule of thumb that coming out of the power supply, we go to the like polarity of the first device. So positive out of the power supply would go positive of the transmitter, negative of the power supply would go to the common of your meter, and then we would connect our negative coming out of the transmitter over to our milliamp input of our meter, and that would be the current loop. But that would be too easy. We don't have anything to adjust the temperature of this thermocouple. So we had to be creative with it. We had to come up with something. We had to create something that would represent or replicate the signal coming out of the sensor itself. So the way we do that is we take a voltage divider, and it's a simple series circuit. We apply power supply, we apply 2 volts DC. And we go through a fixed resistor, the potentiometer, and another fixed resistor, and we use the outside 2 legs of that potentiometer. And if you remember back in DC, I think you guys discussed a potentiometer, but it's a variable resistor. There's an adjustment knob right in the center of it, and there's also a middle leg on this, the 3rd leg, which is internally connected to that adjustment knob. And around the outside, between each leg, all the way around there, is a resistive material. And this is a wiper on here. And when this wiper is connected over on this end, and we follow the current flow, we're going all the way around this resistor, so we're going to have a voltage drop. This is the maximum resistance that this resistor between these two, it will always be there, between those two will be. And if we look at that center leg, from here to here, and we'll call this leg A, B, and C. If we took a voltage drop between B and C right now, we would see that internally this is connected to this wiper, and we're going all the way around that resistive material. So we would have the same voltage drop as what we had across the outside 2 legs. And as we rotate this wiper around the other side in a clockwise direction as we're looking at it, and if we would measure the voltage between A and B, we would see that that voltage starts decreasing, and we can adjust that voltage wherever we needed it. We create this circuit to mimic the millivoltage that's going to be going into our transmitter. Let me repair this a little bit. All right, there we go. We have 2 volts applied. There is a set resistance. If we check from A to C, if we measure it with an ohm meter, we'll find that the total resistance of that potentiometer. And the way we dictate, or the way we determine what these other 2 resistors are, is we take the total resistance of that potentiometer, we multiply it by 5, and that is the value of each one of these resistors here. So for example, if this is a 1K ohm, we multiply that 1K ohm, and that's total resistance A to C. If we multiply that by 5, this resistor is 5K ohms, and this is 5K ohms. We do that so that the majority of this 2 volts is dropped across these 2 resistors. If we calculated this all out, we would find that the voltage drop across this resistor is 0.9 volts. And the voltage drop across this resistor is 0.9 volts. Which, according to Kirchhoff's law, that the sum of all voltage drops in a series circuit equals the applied voltage. If we have 1.8 volts dropped across those 2 resistors, that means total voltage dropped across this one is 0.2 volts. If that's the total voltage, and we can use this center tap in reference to one of these, either A or B, or either A or C, we can adjust that 2 volts all the way, or 0.2 volts, all the way down from 0.2 all the way down to 0. If we look in that cross-reference in the temperature book, we find that a normal operating range coming into the input over here might be 0 to 63 millivolts. So the way we would wire this, and we have to pay attention to polarity. This is positive, this is negative. So that means if we use B and A is going to be more positive than B, simply because it's closer to the positive side. If we use B and C, B is going to be positive, simply because it's closer to the positive terminal. C is closer to the negative terminal. So if I connected, find color here, if I connect A to my positive and B to my negative, I could use my voltmeter and measure across these inputs here and adjust this potentiometer to achieve the millivolts that I'm looking for as an input over here, and reference my current coming over here through the output loop. I could calibrate this transmitter. Now the thing is, you only have 1 meter. That's all you're allowed to use. So you're going to have to use your meter in this application. You're going to have to use your meter to read the milliamps going through this output circuit. You're also going to have to disconnect your meter from there when you change the temperature reference and put it across these 2 terminals to read the millivolts that is going into the transmitter itself. Once you have this millivoltage set, you move your meter back over here